Hey there, and welcome. In this explainer, we're going to tackle a classic physics problem. One where we'll combine the world of forces with the world of electricity, all to find a value that's hiding in plain sight. Let's get into it.
So, here's the setup. We've got two identical spheres, and they're just hanging out on these strings. They've both got a positive charge, so naturally they're pushing each other away. They finally settle into this perfectly balanced state, what we call equilibrium, at a 30-degree angle with exactly 2 centimeters between them. The big question is, what's their mass?
The key to cracking this whole thing is a single concept: static equilibrium. It's a really simple but super powerful idea. All it means is that for an object to be completely still, like our spheres, every single force acting on it has to cancel out perfectly. It's like a cosmic tug-of-war where nobody wins. The net force is zero.
Okay, so we've got to map out every single force at play. And here's a little pro tip. Since the whole setup is symmetrical, we only need to analyze one of the spheres. It makes our life way easier. Let's just focus on the one on the left. So looking at our sphere, you've got 3 main forces to deal with. First, there's its weight, which we call mg, pulling straight down thanks to gravity. Then you've got the tension, T, from the string, which is pulling up and at an angle. And finally, the star of the show, the electric force, Fe, that's pushing it sideways, away from the other positive charge.
All right, we've got our forces lined up. Now comes the fun part, turning this picture into math. To do that, we're going to use a simple XY coordinate system and break these forces down into their horizontal and vertical pieces.
And this is where that whole equilibrium rule becomes our superpower. Because the sphere isn't moving left or right, we know all the horizontal forces have to add up to 0. And because it's not moving up or down, all the vertical forces must also add up to 0. Simple as that.
So let's look at that horizontal tug-of-war. The electric force, Fe, is pushing to the left, but what's pulling it back to the right? Well, it's a component of that string's tension. And with a little trig, we know that horizontal component is just T times the sine of 30 degrees. Since they're balanced, T sine of 30 degrees minus Fe equals 0. That's our first equation.
All right, now let's look up and down the vertical forces. Gravity, P or mg, is pulling straight down. The only thing fighting it is the upward component of the tension. That one is T times the cosine of 30 degrees. And again, they're perfectly balanced. So T cos 30 degrees minus mg equals 0. That's equation number 2.
So what we have now is a classic system of 2 equations. We've got 2 things we don't know: the tension T and the mass m, which is the prize we're after. The whole goal now is to play with these equations until we get m all by itself.
All right, let's roll up our sleeves and do a little algebra. From that first equation, we can easily solve for the tension, T. Now we take that whole expression for T and substitute it into our second equation. The beauty of this is that the T just disappears, leaving us with our target, m. A little bit of rearranging, and since cosine over sine is just cotangent, we end up with this really elegant formula for the mass.
Okay, we're so close, but hang on a second. If you look at our formula, we can't solve for the mass until we actually know the value of the electric force, Fe. So let's take a quick detour and figure that out right now.
And to find that, we need to pull out the big gun of electrostatics, Coulomb's law. This famous formula tells us exactly how strong the push or pull is between any 2 charges, as long as we know what the charges are and how far apart they are. Okay, let's just plug all those numbers right into the formula. We've got Coulomb's constant, our 2 charges, and the distance between them squared. You run the numbers, and bam, we get our electric force, 900 newtons. That is a really significant force pushing those spheres apart. Now that we have this key piece of information, we can go back to our main equation and finally solve for the mass.
All right, this is it. We have all the pieces of the puzzle. We've worked out our formula for the mass, and now we know the electric force is 900 newtons. Let's put it all together.
So here's the final step. We take that 900 Newton force, we multiply it by the cotangent of our 30-degree angle, and then we divide the whole thing by the acceleration due to gravity, which is 9.81. And there it is. The mass of each sphere is 158.9 kilograms. And whoa, just think about that for a second. That is seriously heavy for a little sphere, right? It just goes to show you how unbelievably powerful electrostatic forces can be.
So what's the big lesson here? It's really that any problem that looks this complicated can be solved if you just break it down. You identify the forces, you write down the equations based on the physics, and then you just solve for what you're looking for.